In this video, we're going to do an example of comparing proportions from two independent samples. And these two samples must come from populations that have really nothing that relates the two of them. And to try to make this a little clearer, let me give you two examples of samples that would be considered dependent. Imagine you're taking blood pressure values from patients, and imagine that your first set of samples are from blood pressure readings that you've taken in the morning, and your second sample are going to be blood pressure values readings that you take from the same patients in the evening. Well, we can see there's a natural relationship between those two samples, those two populations, because it's the same patients. We could pair up the results from a patient in the morning with that same patient's results in the evening. So that's an example of dependent samples. So we're dealing with independent samples, which means there's no natural pairing of the results of one sample compared to another sample. That's what we're doing here. All right, here's our example. We're going to test a claim of whether insecticide-treated bed nets actually reduce malaria among infants. Maybe you recently saw an episode of American Idol in which they showed scenes from Africa in which they were passing out to parents of infants and children insecticide-treated bed nets to help reduce the outbreak of malaria. Now, how do we actually know that these insecticide-treated bed nets actually reduce malaria? Well, we're going to take the results of a study and statistically, scientifically, see if we can prove one way or the other whether or not the insecticide-treated bed nets actually work. So, here we go. We're going to start by identifying my populations, my two populations. My first population is going to be infants using the insecticide-treated bed nets. And my second population is going to be infants, obviously, not using the insecticide-treated bed nets. And we're going to test this claim, this hypothesis, at a significance level of 1%. And we will again comment on exactly about what that means later on when we deal with this value of 1%. Now, there are a number of new symbols in this section, just like there have been throughout the quarter, and we need to talk about. Most of them are going to be pretty straightforward because they're similar to what we've seen in the past, but there is one new symbol with a new concept. Okay, let's take the easy ones first. We are going to be calculating a proportion from the first population. And you might recall we used P to represent the proportion of the population. And so we're going to call that P sub 1. The population 2's proportion, then you might guess we're going to call P sub 2. The size of our sample from the first population, well, we normally use the letter N. So for the first sample from the first population, we're going to call that N sub 1. And the size of the sample from the second population we'll call N sub 2. In the past, we have recorded the number of successes that we have in our sample, and we've always used the letter X, so we're going to use X sub 1 to be the number of, quote, successes, whatever those are, from our first sample. And the number of successes from my second sample, of course, we're going to call X sub 2. All right. Now, the proportion that we get from our sample, number 1, is going to be called, like we have in the past, P hat, but we're going to give it a subscript of 1. And we're going to calculate this proportion by taking the number of successes and dividing it by the total size of our sample. In the same way, sample 2, its proportion is called p hat sub 2, and these are all lowercase letters, by the way. Every one of these is a lowercase letter. And that's found by taking the number of successes in our second sample and dividing it by the size of the second sample, which is n sub 2. You should recognize q hat. Q hat is just the complement of p hat. So q hat sub 1 would just be the complement of p hat sub 1. So that's 1 minus p hat sub 1. And of course, q hat sub 2 is just going to be the complement of p hat sub 2. Now, if all these symbols are bothering you here and you're saying, oh man, what are all these new symbols? Well, that means you need to stop this video right now and realize you have not prepared yourself for looking at this video. You need to go to your textbook and read this section. Look through all the symbols, read through what they mean so that you are prepared really to understand this example. I will wait for you. Okay, ready to go? Here we go. The new concept, the new symbol that we have here is what's called the pooled sample proportion. And it's going to be represented, I know the letter P gets overworked, but that's the way it is. This new concept of a pooled sample proportion is going to be represented by P bar, and P bar is equal to the following. Pooled means we put everything together. When we pool things, we put them together. So that means we're going to take the successes that we get from our first sample and add it to the number of successes we get from our second sample and divide that by the total number in the two samples altogether. Imagine taking the two samples and putting everything together, so we would have this total, this many successes, x sub 1 plus x sub 2, divided by the total number, which is n sub 1 over n sub 2. Well, P bar has its own complement, and of course it's going to be called Q bar, and it should be no great surprise that Q bar is going to be calculated as 1 minus P bar. Okay. Now that we got all the new symbols described, let's go on and continue our discussion and test of this claim about the insecticide-treated bed nets. The null and alternate hypothesis. Hopefully you recall that the null hypothesis is always an equality. So our null hypothesis is saying, no, there is no difference between insecticide-treated bed nets and infants that don't use insecticide-treated bed nets. We're saying that these two proportions, P1 and P2, are basically equal. Okay, well, the null hypothesis deals with inequality, and it is going to be our actual original claim that says the insecticide-treated bed nets actually are better. So its claim is going to be that the proportion of children that get malaria from the first population, P sub 1, is going to be smaller than the proportion of children or infants that get malaria from the second population, namely those that are not using the bed nets. Okay, you should recall that we always assume that the null hypothesis is true. So in other words, we're going to assume that P sub 1 does equal P sub 2. And another way of saying that, if these two values are really equal, then we can treat this as a difference and say, well, that difference is just 0. That means there's really no difference between the two. Now, we hope to show that this isn't correct, but this is what we always assume. The distribution that we're going to sketch in just a second is going to be a distribution of all the possible differences between any sample proportion from population 1 and any sample proportion from population 2. And if we're assuming that there is no difference between these populations, then most of those differences should be 0. We'll continue it in the next video.